I would like to welcome Krunoslav Zaher, the creator of RxSwift. It's the first time he's speaking in a big conference, so please be nice and welcome him as you can do. Please welcome Krunoslav Zaher.
Junior presented like he's expecting something bad, so I'm hoping it won't be so bad as he expects. But yeah, so my name is Krunoslav Zaher. I've been working on RxSwift for the past 2 years. I'm the initial committer. So right now I'm kind of in charge of the project. I merge pull requests, kind of decide which direction will we take. And you know, if you have a bug, so I'm probably the person you need to hate on Twitter. So yeah, that's nice. I'm here to actually present you, my personal kind of tour of Rx. What were my experiences with it? How did we use it? How did we solve some complex problems, etc. So these are kind of my personal experiences. Yours might be different. And that's okay. I'm just hoping that maybe some of the concepts we'll present today, you'll have, you'll find a way to make good use of them. Okay. So I think this is an important part to understand that this is a common misconception. Reactive as a term has been, highly popular lately, and it's great, but it also kind of created this false impression that that's something you can opt in or opt out. Reactive, as I see it, is a property of your system. So for example, if you have an iOS app, if you have a button somewhere and you can control when user will click that button or not. It's inherent to the problem that you're solving. So you really can't pull out the reactive properties of your system. The same is like with network connections and some other problems. Basically, it comes down to if you have a code and you're passing a callback, you are writing reactive code. Do you like it or not? So the important thing is once you actually identify that you have a reactive problem at your hand, what are you going to do about that? So one choice would be, to just try to wing it and try to, solve all the complex state machines ad hoc. I wouldn't recommend that. Probably a lot more stable solution would be to use some kind of reactive library, preferably RxSwift. Because we have really over 1,000 unit tests. We have implemented the common operators, and there is a lot smaller chance that you'll find a bug somewhere after using RxSwift than if you were to just write that code in an ad hoc manner. So this is just in case you haven't actually seen how Rx code looks like. It's something like this. Some people like it, some people don't like it, but I think it's really kind of highly readable. So I'll try to explain what is Rx in its core. So it's just a callback. So when you want to teach somebody Rx, this is it. Like this is the entire Rx concept. It's not like a library with 50,000 lines of code. We don't have 50. We have like 10 or something like that. But my point is, it's extremely simple. The only assumption you actually need to have is that you have a system and that it takes a callback, and that's it. Okay, so if you actually take a look at our code base, you'll notice that the interface is a bit different. So why is the interface in RxSwift a bit different than the generic, just send me any message through a callback? The reason is that people have noticed that there are common patterns. So you really want to provide a way for a producer to inform an observer that he has completely generated elements, or there has been some kind of error, and observer should be aware that he won't receive any other messages. So what we've actually done is we've encoded that into the protocol. So you actually don't have to implement like some kind of boring redundant state machines, that deal with errors and completions and things like that, you only need to focus on like a really high-level concept, and that is an observable sequence. So I'm going to explain why, what is the relation between observer and callbacks and observable sequences. It's really simple. You don't need to use some kind of complex math for this. So it's important to understand what happens when you actually subscribe, because the subscribe is the only method on that interface. So it comes down to explain how does it operate. So what happens when you call subscribe, you do two things. You create some kind of private resource, okay? And you pass a callback to that private resource. What you get back is a subscription object, okay? And you can use that subscription object to terminate the connection. You can say, okay, I don't want to receive anything else. So this is how it kind of looks like. So there is a sequence of messages, and those are actually the observable sequences that we are talking about all the time. So a really simple analogy that I've heard being spoken a lot of times is you have a tap, and that tap is kind of dripping water. So when you're registering an observer, what you really are doing, you're catching those kind of droplets, and each droplet is an element, and all drops are the same type. And the subscription object is like when you don't want to actually observe the water, you call this post that is equivalent to actually closing the valve and stopping the water from flowing. So that is kind of similar to what I've just said, but there are two kind of crucial differences. One difference is that until you call subscribe, that there really isn't any tap of water. A tap of water is magically created like out of thin air when you call subscribe. The other difference is that when you actually close the valve, you actually disintegrate the tap. So there is no more tap. So why is this important to understand? It's important to understand because by default, what happens when you call subscription twice? You don't get a single tap of water and you're observing a single tap of water. You actually have two taps of water and you have two separate chains that are handling the events. So that is kind of a common misconception. What you can do is you can use certain operators to say, okay, if there is another subscription, there is another observer, let's share the same tab, it's more efficient. But this is how it behaves by default, okay? So, another thing are the operators. So, you might notice, like the operators are these methods, are these extensions that you see right now on the screen. And in RX, we have a bunch of them. And usually it's a misconception that to really be proficient in RX, you need to know like all of them by heart or something like that. You really don't get statistics which of them are important or common or things like that. So what we're going to do, we actually try to explain that a bit better and to put more commonly used somewhere in some docs. So if you're learning RX, you should focus maybe on these. And the thing is, if you're programming with RX, you should really probably use 10, maybe 15. And a lot of them you already know, like they're equivalent to operators on normal sequences. There's like map, there's filter, flat map, and a lot of familiar ones. Okay, so what is kind of nice about this code? Well, it's declarative. What do I mean by that? You're describing these kind of high-level operations, and it's kind of similar to differences between if you worked in Objective-C code, you'll notice that there's a lot of for loops in Objective-C code. And for example, if you would write a filter function, if you want to do a filter in Swift, you would just call array.filter. So I don't think that anybody really questions that you should call filter, and I don't think that a lot of people actually argue that you should use the old for loop. Why? Because it's readable, you're expressing this high-level intent. But for some reason, when people try to think about reactive code, they don't actually come to the same conclusion. They think that it's actually maybe better if I handle those state machine manually, which is equivalent kind of, okay, let me write that for loop. I don't want this high-level operation, which I never kind of understood what happens, but that's what usually happens. So one property of this code, so if you've used code like this on normal sequences, you'll notice that you can just select code you want. You can easily refactor it into a new method. So you'll get the same properties here. It's really an awesome, if you're writing an RX code, it's really an awesome code for refactoring. You can just notice, oh, I'm repeating these three concepts, maybe I'll name this pattern somehow and just reuse it on a really high level. Okay, so the thing that powers all of this, all of the nice properties, is composition. So, what I mean by composition, if you have an observable sequence and you have another observable sequence, the result will be an observable sequence probably if you're using one of the operators. So that means that the result that you got, you can actually reuse it with the original interfaces, with all of the other APIs if you're using observable sequences. So it's really highly compositional code. If you have an interface that deals with React events in one way, for example, if you have target action pattern, or if you have delegates on another place, like how are you going to reconcile all of that impedance mismatch between those interfaces? Are you going to invent a new type? It really adds a lot of kind of boilerplate. So, cool thing is that RX is kind of closed for a lot of operations. What do I mean by closed? You can apply a lot of operators on observable sequences and get another observable sequences. It's not bulletproof. So, for example, there do exist operations that when you apply an observable sequence, you don't get an observable sequence. For example, you can say, okay, I'll subscribe and I'll block the caller. That obviously is not an observable sequence. But for a lot of kind of practical use cases, you'll do just fine. You'll always get an observable sequence. Okay, and also some other kind of nice properties if you write reactive code in a way like this, is that it's awesome for testing. If you really kind of need to test complex behaviors, you can of course write more fine-grained tests on reducers, but you can also kind of test the entire system. So for example, if you need to test some logic that depends on I don't know, some UI buttons, you don't have to create a UI button. You can just create, you can say observable just, and you have a mouse tap, or tap on the screen. Okay. So the next thing that's kind of nice, so this is a tweet. I'm not trying to say, I found actually this tweet kind of funny. I usually, from time to time go to Twitter and try to see what people are saying about RX. I usually don't respond because I really don't have a lot of time. But I'm really interested, what guys are saying around there. So this was funny because we've kind of put a lot of effort into documentation, and I had an idea, like, I really thought that we were kind of presenting some cool ideas in there, and on the other side, I don't think that people really understood that why those ideas are cool. So I'll, maybe put a lot more effort into explaining them, like this is why I'm here today. So why is it awesome, that we have observable sequences and we are kind of optimized for processing visual information? I think that should be kind of obvious. You can visualize observable sequences pretty easily, right? So, for example, if you have some state machine and you have another state machine, if I were to ask you, okay, can you tell me when you combine those two state machines, what is the third state machine you get? Even if it has like 2 or 3 states, you won't be able to simulate that in your head. At least, people I know can't. Maybe some people can, I don't know. But, it's probably really tiresome. On the other hand, if you have one observable sequence, if you have another observable sequence, it's pretty simple. You can, focus on one element, on the other element. You can figure out, oh, what the result will it be delayed, or will it be some third type of element? it's pretty simple to visualize this thing. So there is, quite a lot of awesome properties that we've noticed. But, if I spent the entire day today telling you how awesome it is to ride a bike, and, I gave you a bike, you still won't know how it's actually to ride it. So it would be great if you could, just, try and play with it and see, can you figure it out? Can you actually, write something useful or not? But yeah, that's kind of the point. So I would also kind of like to share, like, how we use RX. I think that's kind of one thing that was missing online. I think everybody has their own way how they think they should use RX. I think that is awesome. I think that's, I wouldn't want to stop that. I'm just here to share like what was our journey, what are like the good sides, the bad sides, and how we actually try to tackle them. Okay, so a pretty trivial way to use it is data binding. You have tons of examples online. It's nothing fancy, but it's pretty, a common way how to start with it. And it's really useful because, you can with ease bind something to your table view. We have a lot of kind of nice extensions out there. And you can also do it on the other side, like from the UI to your model layer. You can, dispatch easily commands from the UI. And, this will work great. It's really hard to kind of mess this up. So, maybe try with this. So another thing where RX really kind of shines are stateless APIs. I mean, RX originally was invented for server-side use. So I think guys at Microsoft were using it, I don't know, to solve some kind of server API issues because it has a lot of operations for data aggregation, parallel processing, things like that. So you can use it pretty easily for I don't know, making HTTP requests. Yeah, I would say I think there's like RX Moya and some other networking libraries. So also, what I would like to say is that not all problems you're probably going to face are going to be trivial, and not all they weren't even trivial for kind of us. But we've tried to find some ways how to handle them. We actually didn't even insist on RX solution. We were like, just find any solution, and if anything works and it's not RX, it's fine, no problem. So I think like this is a typical problem that doesn't really fit with RX Swift as conventionally thought. Why? Because there is a lot of interaction, right? So you have some state, user sends commands, you want to map that state on the UI, you want to make HTTP calls, but HTTP calls actually depend on the state, and it looks really messy. You don't see any structure in there that is kind of intuitive, right? And we could, make it work, but I wouldn't, feel proud actually, here today and share you the way we've solved this previously. It's not really elegant. I didn't like the solutions we actually made. So next problems we had was actually fairly complex Bluetooth communications. So I'm not sure how many of you actually are working on Bluetooth and trying to connect with the devices. So awesome, I see some people there, so this might be useful for you guys. So, Bluetooth is highly complex. There's a lot of state, there's a lot of resource management, there's a lot of commands, and it's really not too obvious how one should actually hook everything up. And of course, user can send arbitrary commands at arbitrary state. Everything has to be, instantaneous and reactive, of course. So, these kind of issues, we could hack it, but again, not something I feel comfortable sharing how we have done this before. And, you can find probably a lot other problems like data synchronizations. I had problems like you have audio engines. How do you communicate with them? How do you model that? If you have some complex UI state machine logic, you have paging and I don't know, some screen transition maps or something like that. We had problems where we had like our own authentication state in the app, but then we also have Firebase. And you need to find some way, how do you synchronize those states? So you need to choose, okay, this will be master and source of truth, and then we'll try to synchronize the other one somehow. But if this thing can't fail, because if it fails, your system will be in inconsistent state. Okay. So, challenge, besides, those kind of constraints and challenges we faced, we really want to find like some solutions that would be elegant. If we, could find one solution to solve all of these problems, that would be probably a preferable choice. But if not, we would take anything. 2 solutions, perfect, no problem. So we also wanted to find, how some solutions that are straightforward to explain. Because, if you have some new RX user and you try to explain, you should do this or you should do that, it's not really well defined. And, the chances are when you come back and when you see what that person has actually coded, it probably won't be initially too idiomatic and it would maybe be weird. He'll be using his own patterns. But, that's kind of the biggest strength and the biggest problem currently with RX. RX is not an architecture. RX is a tool. And what we actually need to do is we need to figure out how do we design systems with RX in a nice way, because not all systems are unidirectional. So we definitely need to find some solutions that are a bit more generic. So another constraint that's pretty obvious, we can't think of some solution in vacuum that's totally incompatible with existing technologies. Like Bluetooth stack is Bluetooth stack. We need to just figure out how to deal with that. It has to be well defined. I think I kind of already explained that part. Ideally, it would be some kind of code, maybe an operator or some other code if it's not RX solution. And we would really, want to solve not kind of toy examples, but really sophisticated use cases. So, when you present this to someone and say, try to do this without RX, that person would kind of stare at that and say, I'm not sure. But, we can present it, it's not hard to do it with RX. Okay, so the solution I'm going to present, it's basically pretty obvious. It's feedback loops. So we actually figured out that what was causing problems for us were feedback loops. So in case of paging, you had a feedback loop that basically went from state, it would do something, and it would return to state. In case of Bluetooth, it was kind of similar because you had some kind of control state there. UI already had that loop, so that was awesome. But you could model a lot more than what I've just said by using this, because it's a pretty, it seems to me that it's a pretty general concept. And I'm going to try to explain how it actually worked out for us and what were the parts. So for example, if you have paging, you have some state, and state is pure struct. It doesn't contain anything funky there. And you have 3 feedback loops, okay? So you have a feedback loop that goes from state to UI and then back to state. That is the control loop. So when the user is clicking something on the screen, he's actually sending commands back to reducer, and the reducer changes the state. So another feedback loop is kind of we need to load somehow the initial state. And the third one is kind of load previous page when we've hit I don't know, a table view, bottom or top or something like that. We had different calls, so we've just created 2 different feedback loops. And this actually worked out pretty well. I'm going to show you after some code. Like on high level, it's pretty clear. So the next one is probably Bluetooth. And it's pretty similar, right? So you have, in case of Bluetooth, what we actually encoded in state was what is the state of communication with Bluetooth that we actually want. So the way this thing works is, let's say you want to start synchronization from some device. You would conjure up a command, start synchronization, and it would change state, I'm synchronizing. And then, Bluetooth connection loop would actually figure out, oh, I need to start synchronization process, and it would start to, produce commands after a while. UI feedback loop is kind of the same, like I've told you in the paging example. But there is also a bit more here. We've noticed that actually, as you have like this big feedback loops, you also have a small feedback loop. So this thing is actually recursive, which means basically that you can build some kind of fractal systems using it, which is a really, really nice property. But this kind of follows from the composition part, and I'm going to later show you a bit of tiny code so you could get a taste of it. But then we kind of, try to take this even further. So, your entire app is a state and some feedback loops. And this maybe looks silly on first, but this actually helped us while we were refactoring a lot of code, because the terms that we actually didn't know how to name previously, now we just name, oh, it's another feedback loop. Okay, no problem. So right now we have one app that is really close to this. And if you're kind of thinking like two operators, one inside the other, that really kind of doesn't really prove that this is fractal or recursive or even doable. We actually have, like, if you count, more like 5 or 6 levels deep, but you don't think about them. It just comes natural. But when you start to unwind and think like this abstraction has system and this one has and this one has, but the latest maybe even, it's not maybe even explicit operator, but we've kind of hard-coded some state machine inside our communication protocol that we can later refactor. Like on biggest level, we can't really use an operator. We can't store entire state into memory. But what we do is we use the solution as an architecture. So we store state into a database. In our case, we are using some kind of combination between core data and Firebase right now. And we are, those feedback loops, some of them are, just kind of written somewhere, they have the same form, but we've kind of manually started them. But it's the same concept. We've also started to push this on Android. And so far it really shows promise. Okay, so what are the next steps with this? So I would say this is kind of in alpha version right now. So what do I mean by alpha version? I've kind of thought about this for maybe 2 years. So basically I didn't really want to do something like this because I thought, maybe the problems we were facing are a result of some of our bad choices. But you kind of start to doubt that after 2 years, and you really, see those problems appearing over and over again, and you say, maybe there is some kind of pattern that we are missing here. So, we've just decided, well, let's, instead of kind of denying that we have a problem, let's maybe try to consider, okay, maybe this isn't really a big problem as we originally thought, and how can we think, basically, how can we change our way of thinking? So, like I said, 6 months ago, I think I gave up on trying other solutions, and I've tried this. I've tried to first implement it myself in one of our apps. After that, I don't know, I think 3 or 4 months ago, I presented some other developers. A month after that, we've tried it in some other use cases, and it turned out pretty well. So after that, we actually went even further and start pushing it on Android. Right now, we are kind of refactoring 3 apps to use this. And so far, every time we've applied it, it really drastically simplified our code. And I'm really kind of excited because really the positive experience we had with this thing. But that doesn't mean that it's probably bulletproof. I'm just saying that for our use cases, it worked out pretty well. So we have this concept. If you're curious about learning more, there is a system operator inside our example app in the main RxSwift repository. So that is the exact form of the system operator we are actually using in all of our apps. You can maybe now figure out on yourself how does it work, because like I said, this is really alpha stage. We don't have any documentation, so it might be a bit cumbersome to understand some of it. And what we actually have done, we've gone even a bit further, and I think about a month ago, I think I finally, figured out maybe a way how I can, in an easy way share some of the concept and how you should actually design systems using it. But there is still a lot of work. Like first we need to choose a name. I like Rx Fractal, some people hate it. I'm not going to point fingers. So we also have like Rx feedback or maybe some other solution. So if you have some nice suggestion how we should call it and that has a catchy name, feel free to reach out and maybe state your suggestion. So I'm just going to give you a taste like how does usage on a really high level look like, so you can glance it. It basically looks like this. So you have a separation of state, you have a separation of transitions of that state, and you have a separation of effects. So as you might imagine, this is so awesome for unit testing, I really can't emphasize it enough. And the cool thing, the result of this is, of course, an observable sequence. So yeah, thank you for listening to this talk. If you have any questions, I'll be around here, so feel free to ask.